Hey guys, Buildzoid here, and today we're going to be taking a look at another RTX 3080 PCB, this time the RTX 3080 Vulcan from Colorful. Now, before we get into this, the PCB pictures are, of course, from Tech Power Up's review of this card, so if you want more details about it, you should check out their review. There will be a link to that down in the description. And yeah, big thank you to them for providing high-res PCB pictures in their reviews, because, like, a lot of reviewers just don't take cards apart. And then a lot of the time when they do, they don't really do a great job of providing pictures anyway, so yeah. But Tech Power Up does provide really great pictures, so thank you to them for that. And yeah, with that out of the way, let's get into it. So this might look somewhat similar to the RTX 3080 Strix PCB, which I recently declared the best RTX 3080 PCB you can get. There's a video about that. You can go watch it. I'll probably not remember to link that down in the description, but maybe we'll get lucky and it'll end up in the comments somehow. The thing is, at a glance, yes, this does look very similar. I mean, we've got all the molded SMD polymer capacitors on the output filter. Actually, this has better input filtering capacitors because this is on tantalum polymers on the input filtering. Not that that really matters too much. The input filtering really doesn't need to deal with as fast transients as the output filtering does. So there having super low ESL capacitors isn't as important as having them on the output. And this does have a lot of phases. In fact, this has more phases than basically any other 3080 PCB I'm aware of. This is probably actually, not most phases, that's the wrong term. It has the most power stages of any RTX 3080 PCB I'm aware of. But of course, not all power stages are equal. Not all power stages are, created equal, so that doesn't really, in and of itself, mean much. And then, of course, there's also the voltage controllers, which we have to get to. And that's actually where we get a lot of the differences, is in the power stages on this card and the voltage controllers. So, anyway, let's go over how this monstrosity of a VRM is laid out, because Colorful had to get seriously creative to get all these power stages onto this PCB. Probably because there's heatsink clearance concerns up at the top edge. Technically there's probably enough space that they could have whacked this power stage over there, but they didn't, and I'm assuming it's to make way for those screw holes. But anyway, so did I overshoot? Yeah, I kind of overshot that line. So this right here is a mix of memory, uncore, and vcore, because of course. So this bottom phase is memory power. And the 4 phases above that, and these are actually 4 separate phases, these are the MSVDD rail, or what I like to refer to as the uncore. I suspect the MS stands for memory system, which is really misleading because most people would think, oh, you mean the GDDR? No, not the GDDR6X memory chips. This actually powers this lower section of the GPU core, or at least primarily powers that lower section of the GPU core. There's a bunch of memory controller and cache related stuff in that area, but since it does memory controller things, and the memory controller, the actual GDDR6X memory controllers themselves are right along the edge of the die, which is, to match the layout of the memory chips, this probably also provides power to the outer edges of the die. But the main point is this is not the main core power rail. Also, it's unique to the GA102 chips. The smaller chips, because they're smaller, don't need a dedicated MSVDD rail. MSVDD is just combined with the core rail on those, which yeah, I assume here the MSVDD portion of the chip is so big that it made sense to give it its own power delivery region in order to improve efficiency, because you could run this at lower voltage than core voltage or higher voltage than core voltage, and balance the power distribution into the chip a bit better that way. Anyway, and then all of this up here is vcore, which is pretty unique, because normally up at the top of this you'd expect to see a memory phase, but Colorful, I keep wanting to say power color, because color and colorful, and it's just no, this is Colorful, and Power Color makes AMD cards. They do not make NVIDIA cards. But yeah, the rest of this up here is core power. I don't know how many phases we're looking at, because NVIDIA cards have a weird habit of having way too many power stages relative to how many phases their controllers can handle. Then we have this over here, which is more memory power. So that's where our memory phase went. Then this up here is more memory power. So this is on par with like RTX 3090s in terms of the sheer number of memory power in the sheer number of memory power stages, which is not a bad thing. Though it is probably a bit excessive. Then again, I think Colorful's design goals with this card was to just have a very substantial looking power delivery system, not necessarily prioritizing if it's practical or anything. And it doesn't hurt anything to have more power stages, right? And anyway, on this side of the card, we find more core, more uncore, and more memory power, because of course we do. That's how RTX, that's just how GA102 GPUs do. So this right here is more MSVDD. Then we have one phase of memory over here, which this is sort of the memory phase you'd expect to see on most 3080s, and then this one also adds this over here, or I guess this. Nah, this is the sort of additional one. But anyway, so we get memory, and then on top of that, it's just more core power again, or what NVIDIA likes to call NVDDD. Yeah, and also NVIDIA likes to call the memory rail FBVDD for frame buffer VDD, which refers to the actual memory chips themselves, as well as the memory controllers, because memory signals are sent at memory voltage. Like that's part of memory signal. Like the voltage that the memory chips run at is also used for sending some of the memory signals. So yeah, the memory controllers obviously get fed mem voltage as well. Anyway, so in terms of power stages, what we've got here is 14 power stage V-core, and this makes me very suspicious that this is actually a 7-phase and not an 8-phase, because it would make the trade-off in performance, the trade-off from going from a 8-phase to a 7-phase is negligible, because as your phase count increases, the benefits of adding more phases get smaller and smaller. You get diminishing returns. So going from like a 4-phase to a 6-phase, pretty significant upgrade. Going from a 6 to a 7, not really. 7 to 8, even less so. And then once you get into the really ridiculous phase counts, that's where we're kind of just like that's where in my opinion, the manufacturers are just kind of flexing, like, look at how many phases we can get. Though there are arguably some minor benefits, but they're so minor that they're just not really worth acknowledging at that point. But yeah, so we've got a 14 power stage V-core, and actually it's smart power stages, so I could have done that. And then we've got an 8 smart power stage MSVDD. And then we've got a 4 DRMOS component, so that's technically a type of power stage for the... let's use the NVIDIA terminology, FBVDD. So there is a lot of power stages on here, right? Like we've got 14 in the V-core, which is, I think, as high as it gets on 30 series cards in general. Like, I don't think you can even find a 3090 with more power stages than that. The MSVDD definitely, like, you do not get more than 8 smart power stages on an MSVDD rail on any card that I've seen. This is absolutely, like, quantity-wise, this is ridiculous. This is as big as the V-core of a reference 3080. Actually, it's as big as the reference 3090 V-core because, so this is gigantic. This is absolutely huge. And then we have the 4-phase memory rail, which again is just like there's no card with more than 4 phases for memory power. So absolutely huge number of phases and power stages on this card, mostly thanks to the MSVDD, because again, the V-core might be a 7-phase. It would certainly simplify the design a lot and not really have any major downsides to it, especially when, Colorful is buying all these expensive tantalum polymer capacitors for the input filtering. Like, you don't even really need to worry about the ripple from the VRM too much. And even there, like, the main concern is the actual transients, not the switching noise from the VRM itself. Like that, the switching noise of the VRM is just completely dwarfed by what the GPU core produces. Anytime it decides to go from one level of power draw to another. So Anyway, yeah, lots and lots of power stages. What are they controlled by? Well, well, I wasn't really hinting at it, but it's probably easy to guess that, wait, screw it. This runs on UP9512s. I keep trying to be way too fancy with my explanations. Like, why do I bother? 9512s for everything. So this is sort of the first big difference that we see between this and the Strix, right? The Strix also has kind of a lot of power stages, very powerful rails, and uses smart power stages. We've still not gotten to the part where we talk about what smart power stages, but they are smart on both cards. But the controllers are a big difference. So the Strix card uses MP2888s, which are basically the best, like one of the best voltage controllers you can get on a 30 series card. The UP9512 is basic, like this is a case of like, I guess it's not a 9511, which is like the bare minimum. Because yeah, the 9512 is pretty much a 9511 with some minor upgrades done. So it can go to higher switching frequencies. This will go up to 1.2 megahertz. Not that that's useful, unless you want to turn your VRM, unless you want to make your VRM really inefficient. Yeah, so it goes up to higher switching frequencies than the 9511. It adds some very basic digital functionality that the 9511 didn't have at all. But for the most part, this is still a very analog chip. So if you wanted to mod this card, you could modify basically everything on this card by just using potentiometers and resistors. You want to change the switching frequency, you just need to set the resistance on a pin of the UP9512 correctly. You want to change the load line, also controlled by a resistance on one of the pins of the 9512. You want to change the V-core or any of the voltages, again, you can just add a potentiometer to tweak the ref in pin of the 9512. So basically, from a hard modding perspective, arguably an easier chip to work with than the MP2888, because the MP2888 is fully digital, but the MP2888 also goes up to 10 phases, whereas these are 8-phase controllers. The MP2888 also goes up to way higher switching frequencies, and is just, on paper, it should just generally be a more advanced voltage controller than the 9512s that we have here. But as for what that does for voltage regulation performance, you'd actually have to ask an oscilloscope, because obviously there's more to there's more to voltage regulation than that just what voltage controller you're using. It's affected by what capacitors are used, how they're configured, what power stages, what inductors. So there's a lot more to it than just like these controllers are much cheaper and much worse than the ones that you see on the Strix card. That doesn't necessarily mean this is going to have a significant impact on real-world performance. It's just a case of like, yeah, these are cheaper voltage controllers from UPI Semiconductor. And if you were thinking of like hooking up an Elmore EVC2 or something to them for voltage control, you do get some, but it's very limited. It's not going to be like you're not going to have as much control as you would get with an MP2888. Yeah, so we have two 9512s on the back, one of them for V-Core, one of them for MSVDD. Then we have a miniaturized 9512, which is this right here. That's another 9512, and you might be like, isn't that a little small? No, it isn't. So UPI, what they do is instead of making a new like a separate 4-phase controller, they just take the 9512 and they put it into a smaller chip, like into a smaller package. The chip is physically smaller, and the end result of that is like there's not enough pins to have 8 PWM signal outputs and then also the current sensing inputs that are necessary for an 8-phase controller. So this right here is a 4-phase variant because it doesn't have the extra pins and also saves some board space. So yeah, so this is the 4-phase variant of the 9512, but internally it's probably exactly the same as an 8-phase 9512. It's just not all the connections available are used. And that handles the memory VRM. So that's sort of what's handling all the controls on this card, is just, 9512s for everything. So at least they're not 9511s. I guess you could make that argument. Not that I think there's anything wrong with the 9511, but well, no, like the 95, as far as I know, the 9512 should basically be the exact same thing as a 9511 with just some like updates to support more modern GPU designs, but actually not even that. Like it's literally just more switching frequency, which you never see in use because your VR, like if you run a VRM at much more than 500 kilohertz switching frequency, it gets insanely hot. For very negligible gains in terms of, well, anything. And from the factory, your goal with a VRM isn't like, you know, your goal, you can improve voltage regulation with the higher switching frequencies, but most circumstances, the priority isn't that. It's making a VRM that doesn't overheat and die. So, yeah, most cards ship with a switching frequency of like 300 to 500 kilohertz, and the 9512 just doesn't really give you an advantage there. And then you do get the I2C functionality, but that's not accessible on NVIDIA cards anyway, so yeah. Honestly, not entirely sure why they opted to go with the 95. I'm actually really surprised we don't see a ton of 3080s using the 9511, though I guess that's all the reference cards, because that's where you normally see the 9511, and also the 9511 and 9512 are technically, I'm actually not sure if they're pin compatible or if it's just the 3080, the PCB is actually designed so that you can reconfigure it for both chips, because there's like, you can get NVIDIA PCBs with, actually, yeah, that's probably what's going on, because you can see how there's so many unpopulated component pads all around our voltage controllers. So that's probably so that if there's not enough 9512s to use, they can just switch over to a 9511. Or an NCP, there's a NCP 8, what is it? 81610? Something like that. There's an NCP chip that's also interchangeable with a 9512, at least on NVIDIA cards, if you reconfigure all the passives around them. So yeah, that's kind of fun. So I guess like this might be a 9512 variant. There might be a 9511 variant of this card as well. You can't do this with the cards based on the MP2888, or at least you won't see that done because those normally are designed to run in 10-phase mode, not 8-phase mode, and all of the controllers that you can sort of interchange, they're all still 8-phase controllers. So they make that a lot simpler. Anyway, where was I going with this? Well, so that's the control scheme here, and that's sort of the first big difference against the Strix, is just this is using cheaper voltage controllers that might deliver slightly worse voltage regulation, but again, there's more to it than just what controller is used. Then for the power stages, this is the next big difference between the Strix and, well, this. This uses NCP 30, 31, 51 power stages, smart power stages. And these are 50 amp smart power stages. And so these are another sort of odd choice from Colorful. Or you could initially think they're an odd choice because the reference NVIDIA design, like these power stages right here, those are 50 amp DRMOS components. And so you might be looking at this and going like, why would you go from, like the reference design uses 50 amp DRMOS components for the entire vCore, entire everything. Everything is 50 amp DRMOS components. Or, well, actually, these recently got relabeled as 55 amp. So, but anyway, point still stands. Like the reference design would just use the same power stages that they use for memory for everything. This, on the other hand, uses these smart power stages, but they're not any more efficient because they're still in that same performance category of a 50 amp power stage. And so, while this does have a lot of vCore power stages, in terms of actual efficiency compared to something like the RTX 3080 Strix, this is worse. As at 1 volt output voltage, and mind you, when I did the Strix video, that was done entirely at 1.2 volts output voltages because the documentation for those, well, actually, I couldn't find the exact power stage that Asus was using, so I used a similarly rated power stage from the same manufacturer, and those were all spec'd at 1.2 volts, 500 kilohertz switching frequency. These are spec'd at 1 volt, 500 kilohertz switching frequency, and the reason that is significant is that with basically all power stages, as you go from 1 volt output voltage to 1.2 volts output voltage, your heat output will increase. So the heat output figures that I'm going to be writing here are actually, like, if they were scaled up to 1.2 volts, they should be even worse than what they actually are, but I'm not going to, I've not done that because there's no voltage scaling curve in the documentation for these. So, yeah, I'm not just, I've just decided I'm not going to bother, trying to guesstimate where exactly they would end up in terms of heat output at 1.2 volts. It shouldn't be a huge difference, but it is something to keep in mind, is like, since the Strix was done at 1.2 volts, it actually like, if that was rated at 1 volt instead of 1.2 volts, it would have been even better than it was when in that video. Anyway, let's go through this. So 200 amps output on the 14 power stage V-Core VRM should produce about 17 watts of heat, which is certainly not bad. It's just not on par with the Strix. And then 300 amps output, you're looking at 27 watts of heat. Like, the thing to keep in mind is this is still absolutely demolishing every reference 3080 there is, because as I mentioned earlier, reference 3080s use 50 amp parts, and they only use 8 of them, not 14. And there's more benefits to it than just the efficiency gains. Just spreading the heat load across 14 power stages instead of 8 will significantly reduce the operating temperatures of the VRM, assuming that they're like implemented correctly, because there are technically ways that you could have a lot of power stages and still get them to run really, really hot, but you'd kind of have to be trying to make your VRM do that. But anyway, so assuming these are properly set up, like, this is just going to be, this is way better than a reference design from a current handling capacity perspective, even though it is still behind the Strix on an efficiency standpoint, from an efficiency perspective. 400 amps output, it's going to be producing about 42 watts of heat. And 500 amps output, it's going to be producing about 64 watts of heat. And 600 amps output, it's going to be producing about 97 watts of heat. So, you know, for daily use, you should never really see power current draw above 400 amps. Honestly, I'd be very surprised if you even got to that. And this is definitely, like, this isn't an extreme overclocking card. Like, I mean, you could take this on LN2, and it's certainly, like, if you couldn't find a Strix and this was the next best, like, this is the next best thing. And if you wanted to take this on LN2, you could certainly, there's worse options out there, way worse options, like actual reference 3080s. Those are a horrible idea. Or a Founders Edition, that's also not a great idea. So, yeah, if we take it from that perspective, it's like, you know, yeah, second place to the Strix is not a bad position to be in. And yeah, this would certainly be capable of doing some LN2 overclocking, but this Strix does have a efficiency advantage, which also means for, you know, benchmarks, the VRM is going to, like, the thing is, you can still get away with insanely high heat outputs in 3D benchmarking or, like, in extreme overclocking by just not running long benchmarks. And in day-to-day usage, this VRM is more than enough. Like, way more than enough. You'd really have to be trying to, well, if you're not going to mod the card, I can't see any way that you'd be averaging 400 amps of output current from the VRM. Your card would have to be pulling in excess of 600 watts sustained to be getting into that territory, right? Because you obviously have the output current, and then the heat out, like the power losses on the VRM itself, and then you have like the MSVDD rail and all the other things on and the memory rail and the power that it provides. So your card would have to be like averaging an insanely high level of power draw in order to be pulling 400 amps from the V-Core VRM. So for day-to-day usage, yeah, this is great. Like, this really is a very, very capable power delivery system. It's just also somewhat behind the Strix design from Asus. Anyway, for the MSVDD rail, we've got a sort of different situation, as the Strix only uses a 6-phase MSVDD, and going from a, like, the thing is, the Strix has a 12-phase V-Core, this has a 12 power stage V-Core, this has a 14 power stage V-Core. So the difference between having, you know, 14 50 amp power stages and 12 60 amp smart power stages, not that big, right? Like, this doesn't have such an insane amount more power stages that it can negate the lower efficiency of each individual power stage. But with the MSVDD rail, that's not so much the case, because this has 33% more MSVDD power stages. So actually on the MSVDD rail, this is a very, very powerful card just in general. So 1 volt output voltage for MSVDD, again, because it's the same parts, 500 kilohertz switching frequency, you'd be looking at 100 amps output, producing about 9 watts of heat, 150 amps output, producing about 14 watts of heat, and 200 amps output, producing about 22 watts of heat, and 300 amps output, producing about 43 watts of heat. I think you're probably going to stay in this area for day-to-day usage. I have no, like, unfortunately, I don't have a lot of, there's not a lot of detailed information for how much power every rail on a 3090 pulls, because fun fact, NVIDIA has all this current monitoring circuitry, but it doesn't actually tell you where that power is going. It's not super, like, it's not designed to do that. Like, that's not what it's even meant to do. Because, yeah, so unfortunately, and so theoretically, you'd need to get like a card with MP2888s for everything, and just ask the MP2888s for where, like, how much power they are handling, which would actually give you a pretty accurate reading, because one of the big benefits of smart power stages is that they give you a very accurate current reading directly from the VRM. And they also have a bunch of cool, neat safety features, and that's actually probably why Colorful here decided to use these, because they could have achieved these kinds of, power efficiency figures just using regular DRMOS components. But if you use DRMOS components, you actually have to do current sensing through DCR current sensing. So use the resistance of the DC resistance of the inductor to do your current sensing measurements. Oh yeah, here you can see the DCR circuitry right here. Which they're using on the memory rail, because they're using DRMOS components instead of smart power stages. Now, if you're doing this for 14 different, power stages, that kind of adds a lot of complexity to the PCB. So I really think the main reason that this card uses a bunch of smart power stages is to simplify the PCB design, and that's why they're still 50 amps. It wasn't like Colorful was like, hey, we really need some crazy high output power stages. It was just like, we want we want to build a big VRM, and then we want to keep it kind of simple, use the smart power stages, because they massively simplify getting current readings from the VRM. You need less passive components, and yeah, that's reason enough to use them, assuming that, you're because the smart power stages are obviously going to be more expensive, but if you're making a more expensive card, then it's like, yeah, that seems like a reasonable trade-off. So yeah, so basically, smart power stages basically for the actual smart features, instead of getting some kind of crazy efficiency like you can get out of the, say, 60 amp smart power stages, 70 amp smart power stages. There's even 90 amp smart power stages out there. Actually, yeah, 90 amp. I think the 100 amp power stages are DRMOS again, so not that smart. And yeah, accurate current monitoring, accurate temperature monitoring built in, all like overcurrent protection, short circuit protection, bunch of protection features. I can't remember all of them, and I didn't put them in my notes, but yeah. So basically, we have a smart VRM, though not super efficient, is one way to put it. And then for the memory, I mean, we're just looking at a bunch of 50 amp DRMOS components in a 4-phase configuration, which is what you see on a lot of RTX 3090s, not 3080s. 3080s normally use a 3-phase memory VRM. Also using these same components, and these are Alpha and Omega Semiconductor AOZ 5311s. And these, so what's really funny about these is when the 30 series launched, the data sheets from Alpha and Omega Semiconductor for these DRMOS components said 50 amp DRMOS component. If you download the latest version of the data sheet for these components, it's now up to 55 amps nominal current rating. So that's great. If you ever wondered about how useless the nominal current spec on power stages is, that should give you some idea of just how useless it is. So yeah, they've just kind of decided to increase the nominal current spec by 5 amps. I have no idea why. The efficiency curves in the documentation are still the same. Maybe I don't know. Either way, it doesn't really matter, because with any power stage, the nominal current rating is kind of more of a performance class indicator than it is a useful performance metric. You do not want to be running 50 amps through a 50 amp power stage, and you certainly don't want to be running 70 amps through a 70 amp power stage, because while it is technically possible for the power stage to do that, the efficiency at that point is horrendous. And you shouldn't do that. It'll run insanely hot, and you'll need way too much of it. Like, you'll need an insane cooling system, and it's horribly impractical. And if you try to put several of them next to each other in parallel, it's just going to be a disaster. Don't do that. It's a nominal, like, the nominal current rating is more like a general performance indicator than it is a actual useful, like I said, it's not a useful performance metric. It's just a rough indicator of how the power stage might perform at lower currents where you're actually going to use it. So anyway, yeah, these got bumped up to 55 amps now, which is just like, I think this is the first time I've seen this happen. Like, I have seen revisions of documentation in the past. Like, there's two different variants of the IR3553 datasheet. There's like a pre-release variant, which had really high efficiency on it. And then there's the final release version, and all the efficiency curves came down. But, or I think it's that. There's two variants of the 3553 datasheet that I have. Do I have both of them? I might have both of them. And yeah, so one of the versions has like way better efficiency curves than the other, and the worst one is actually the one that's like applies to the final retail parts, if I remember correctly. So yeah, but the thing is, that was like a pre-release data sheet, so that was like, oh, this is what we're aiming for, and then it was like, yeah, that didn't work out. But they never changed the current spec. Like, it was always going to be a 40 amp power stage. And it was just like it was just the performance curves that changed. Whereas here we have the performance curves didn't change at all. They're still the same. And they just bumped up the nominal current rating. Incidentally, the documentation for these, the performance curves stop at 40 amps. So they never even told you how much heat these produce when you run 50 amps through them. So yeah, which is normal. Like 60, like if you have like a 70 amp smart power stage, the data sheet probably stops at 50 amps or 60 amps. It won't stop at 70. Like, again, you're not supposed to be running that much current through it. But anyway, yeah, so let's talk about the memory efficiency, which is of course great because it's huge. Like, it's a huge memory VRM. So 1 volt output voltage, 500 kilohertz switching frequency, and yes, I'm aware the memory does not run on 1 volt. It runs on 1.35, but I, again, don't feel like rescaling the output voltages for these parts, especially since there's no voltage scaling curves for them. So, or, well, it's not usually, like, usually it's not a voltage scaling curve, it's more of a voltage scaling line, but still, it can have different slopes depending on the component, so I'm still not going to just rescale, like, yeah, not going to rescale it. Also, it wouldn't make that much of a difference. 40 amps output from the memory VRM, and do keep in mind the memory VRM is really scattered all around the board, which is just to optimize power delivery to all the memory chips, right, because you've got memory chips everywhere, so it's better if you have at least some of the VRM near to each memory chip. Anyway, 40 amps, 4 watts of heat, 80 amps, about 8 watts of heat, 120 amps, about 14 watts of heat, and then 160 amps, about 26 watts of heat. So yeah, like, you can kind of see it here. This is over 6 watts of heat output per power stage. And that should give you some idea of why you shouldn't run 50 amps through a 50 amp, or like 55 amps through a 55 amp component, because at 40 amps, it's already producing 6 watts of heat. At 55 amps, it would probably be producing about 9. It would get insanely hot. Especially if it's like sitting in the middle of a VRM surrounded by other hot running components, right? So, yeah. Anyway, very powerful memory VRM. Like, it doesn't... Well, technically, I think there are cards that have more powerful memory VRMs in the sense that they have, like, 7... I think the Kingpin edition has 70 amp power stages in its memory VRM. Not that that really does anything, because while the GDDR6X runs very hot, it doesn't really pull that much power. It just runs really hot because it's hard to cool. But, yeah... After all, these memory chip packages aren't exactly made out of the most thermally conductive material. I wonder if we'll ever see, like, exposed silicon memory chips. Like if we keep doing these insane GDDR standards that keep pulling more and more power in order to get more and more speed, are we gonna have bare silicon memory chips eventually, or like shaved memory chips where instead of just having a black rectangle, you'll have a black rectangle with the actual silicon die visible in the center of it? Because yeah, this material is not ideal for thermals. Um, anyway. Which is like, there's a reason CPUs don't come in that packaging, or memory chip or GPU cores don't come in that packaging. Is like this is meant for low power devices, and yeah, GDDR6X really seems to be pushing the limits of that. But anyway, yeah, so very powerful memory VRM, vCore also very powerful. I mean, yes, I've been, moaning about it's not as good as the Strix, but it is still way better than the vast majority of 3080s out there, because most 3080s use reference PCBs, and those are, well, those have 8 power stages with the same nominal current spec. Actually, current 855 amp, like, you get the idea. So yeah, honestly, a very, very solid PCB design from Colorful, and like VRM design from Colorful. For power monitoring, we have the usual NVIDIA situation of way too many shunts, right? We've got the three, so these are reasonable, right? You want to know how much power is going through each of your power connectors, you put a shunt for each of your power connectors, but then what the hell is this? And what the hell is that? And especially since, like, we have a shunt right here to monitor the PCIe slot. What are the other ones for? And why are they there? Oh, and then we've got a shunt here. And a shunt there. And here. And I'm not even sure these are actually monitored, because these are 1 milliohm each. I get the feeling these are actually just jumpers, but can never be too sure with NVIDIA cards, because why would you have a simple power delivery? Why would you have simple power distribution if you can have very, very complicated power distribution? And then we have another shunt over here, and these are all monitored by these chips over here, and you can actually read that part number. That is a 45491. And what's neat about these is these have a public data sheet. So if you want to like mod the current readings like really hard, as in fake the power readings completely, you can just do that by disconnecting the 45491 from the shunts and then feeding it fake voltage readings. Because all this does is it just measures the voltage drop across a shunt resistor and calculates the current through the shunt resistor based on that. Well, you can fake that voltage drop quite easily. So, if you ever want to completely disable the power monitoring on any NVIDIA GPU that uses a 45491, well, you can just look up the data sheet on Google, and then you just fake that voltage drop of the shunt resistor, and bam, you've got no more power limit. But you do need to disconnect it first, right? Because if you set up your fake voltage reading in parallel, then that's not going to work. Anyway, what else is there? I guess since this is a 3080, we may as well mention the capacitor configuration behind the core. This is not the bare minimum. This is not NVIDIA's bare minimum specification is that you use like 220 microfarad polymer caps behind the core, and then I'm not even sure that they require the multi-layer ceramics. I know they don't, because there's cards without them. But yeah, they basically require 220 microfarad. These are 330s, so we've got a bit more capacitance. We might even have a lower ESR. I don't know, without knowing exactly which capacitors are in use. It's hard to say. Then we do have some multi-layer ceramics mixed in. However, like most 3080s, this doesn't bother with a bunch of the optional capacitors. And I call them optional because the vast majority of the cards don't have these, right? Like you can see all these unpopulated capacitor pads, and there are some cards that choose to populate those, but the vast majority of cards don't have those. I'm not sure how significant that is, but probably not very. Since the vast majority of cards don't bother with them. Like even a lot of extreme overclocking cards don't bother with those extra capacitors. So yeah, that's it for the RTX 3080 Vulcan PCB from Colorful. I guess I should have mentioned there's another NCP 45491 on the front of the card, because each of those NCP 45491s only monitors 4 shunts. And I think there's 9 shunts in total on this card, so that really makes me think that some of them are just jumpers and not actually being used to measure anything. But again, you never know with NVIDIA. You never know. But yeah, so Vulcan RTX 3080 from Colorful. solid capacitor configuration. I think the tantalums on the input filter are a little bit unnecessary, but they don't hurt. I just think they're an unnecessary expense. But they certainly don't hurt anything, so those are good. Then the fact that we have all SMD molded polymers on the output filter, that's great. You literally, like, when it comes to output filtering bulk capacitors, you don't get better capacitors than molded polymers for output filtering. Like through-hole capacitors just have way more ESL, and when you're dealing with the kind of very fast transients that a GPU core produces literally every time it renders a frame, those just don't do that great a job compared to molded polymer capacitors like we see here. Then for the power stages, I mean, I was really, like, when I first saw this card, I got really excited because I saw that rectangular smart power stage package, and I was like, oh, this is going to be on like 70 amp power stages or something. It's on 50s. But there's still so many of them that the actual VRM current handling capacity is still very, very high, even if the power stages aren't really as impressive as you might initially think they would be, because they do look a lot like they use the exact same packaging that a lot of the 60, 70, 90 amp smart power stages use. So yeah, but these are just 50s. I didn't even know they made 50s in this packaging, but of course they do, because, you know, like, the no harm in having more options for shapes and sizes of your chips. So yeah, and then that's it. Oh, and then the voltage controllers are UP9512s, which are not the bare minimum of what you could equip a 3080 with. So I guess, yeah, it's kind of an interesting mix of parts here, but certainly I don't like it. It's a lot better than reference. It's a lot better than reference. So yeah, that's it for this video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. There's a link to that down in the description below as well. Both the Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you check them out. And yeah, that's it for the video. Thanks for watching, and goodbye.